All right, so topic 5, differential equations. Let's do a quick, like 3-line summary up here for differential equations. Frequently, it's paired with slope fields. In fact, if you turn the page, number 3 has a slope field to go with the differential equation. So a lot of times, if you see a slope field on a free response question, like the first thing you do is probably kind of glance through, it's probably also a differential equation problem. And then the process, this is where we had our silly separate, right, get the x's and y's, separate x's and y's, and then integrate both sides. And then usually there's some information you can solve for C. And that was where we tried to come up with a silly word that also rhymed with separate and integrate. Algebraificate. Solve for C, acate. I don't know. Separate, integrate, solve for C. And then I guess I'd say usually they ask one more question. Answer the question. It's like they give you all this information, you got to do all of that stuff, and then they say, and oh yeah, at time 10, how many bears were in the woods, or whatever. That's usually the process for these. And so they make really good free response questions because you can split those up and get all kinds of points from them. Okay, so let's start number 1. Since you're doing this one with me, let's do it on your own paper. Some of you like to try to squeeze in the free response stuff. Let's don't do that. So separate sheet of paper for these because they're just too much to try to squeeze in. Again, on the test day, like each piece of the problem is usually on a fourth of a page or a half of a page. So these are way spread out. So this problem number 1 is probably on 1 page or 2 pages side by side like that. Is usually how they're sort of oriented. So there's plenty of room to work, and you can also kind of see all the problem all at once, so you're not like flipping around. You work in the book for the free response question, so you can write on the the problem statement and circle things and label things or whatever. So I don't want to say they make it easy, but they make it a little bit more convenient. Obviously more convenient than I've made it for you here. All right, this first one. Again, BC, that just means it was also on the BC test. But there's always, I forget the number, it's 2 or 3 that are on both AB and BC. And so this would have been on both. This is one that when people came out of the test, they were talking about, oh my gosh, the potato problem was awful. And then, like, you're not supposed to say stuff on Twitter or social media after the test until they release it, which is only in a few days. But every year, you go on Twitter and you search for AP Calc or something like that, and students are making veiled references to the free response questions. Oh, that test boiled me alive or something like that. And you're like, if you took the test, you know what they're referencing, and they're, it's kind of skirting the line. But I guess if they don't reveal anything, it's not that big a deal. Anyway, it's silly math humor that people are engaging in, and it is kind of funny. All right, let's actually do this problem now. At t equals 0, a boiled potato is taken from a pot on a stove and left to cool in a kitchen. The internal temperature of the potato is 91 degrees at time 0. Okay, like that's an initial time. I don't know if you've done enough of these, but that's probably going to be used to find C. Right? After we separate and integrate and move things around and solve and do all sorts of stuff, at some point we're going to plug in 0 for T and 91 for temperature, which also means we got to be careful with T and T here, and we'll probably use this to solve for C. The internal temperature of the potato is greater than 27 degrees C for all times. The initial temperature of the potato at time t minutes can be modeled by the function, the internal temperature of the potato can be modeled by this function, and they're telling us that H is the degree, so we don't have to worry about capital T and lowercase t, just H for, I don't know why H for how hot it is maybe. H is measured in Celsius, and here they even spell it out for you. H of 0 is 91. You're like, well, yes, I got that already, but they wanted to make sure you didn't miss that. Okay, so do you understand the setup here? We pull it out of the oven. It's at 91 degrees Celsius. It's presumably going to start cooling down because it starts at 91. It stays greater than 27 for all time. This is Newton's law of cooling. You don't have to know that. And I think I remember saying that if they need you to use it, they'll give it to you. So there it is. We've done those problems, and they didn't even call it Newton's law of cooling. So it doesn't matter if you recognize that or not. But this is how it cools, the rate of its cooling. Okay, write an equation for the line tangent to the graph. So let's see, this is FRQ5, number 1. Maybe I should write some stuff down before I start solving this. I think the main thing would be H of 0 is 91, and the H dt is negative 1/4 H minus 27. Okay, part A. Write an equation for the line tangent to the graph. So a tangent line, I'm already thinking I need slope and a point at time 0. Use this equation to approximate the internal temperature of the potato at time 3. Okay, so I need a slope and a point at time 0. Well, at T0, they already gave me that one. 0.91. There's my point. And my slope is dh dt, which is negative 1/4 H minus 27. So do I know what H is? 91. Let's see, negative 1/4. 91 minus 27. I'm seeing this is a no calculator thing. So I could just leave that as the slope. That's perfectly okay to write the equation with that as the slope. I feel like the trade-off is that's really messy and hard to keep up with. So I'm going to try to take it a little farther even without a calculator and see what happens. I expect that they do me favors here. And sure enough, 64 divided by 4 is 16. So yes, you can continue to write all of that as your safe stop slope, but they made it simplify for you. So slope is negative 16. My point is 0.91. So let's be careful. I'm not really doing y and x. I need to be doing h and t. So normally it's y minus y1 equals m times x minus x1. But we're in h's, so h minus 91 equals negative 16 times x minus 0. Write an equation for the tangent line. So there's my tangent line equation. Now you don't have to box it and you don't have to label it, but that's almost more for me than it is for the grader. I found the first part, that's what it is. Use that equation to approximate the internal temperature at time 3. Oh, I made a small mistake here, and it's a mistake that people ask about probably once a month on my little Facebook group. You see the minor mistake that I made? Good news is you would not get counted off for it. It's that minor. That's supposed to be a T. And the main guy, people ask this question once a month in the Facebook group. What happens if students, mix up their X's and T's? And the chief guy that moderates this group, his answer is always, well, if you tilt your head a little bit, an X looks like a T, so you're fine. So they're not going to get you for that. Find the temperature at time 3. Okay, so H at 3 is approximately, because this is an approximation, negative 16, 3 minus 0, and I'm going to move the 91 over, and hey, there's safe stop. I don't really want to mess with that. I mean, I could, but why bother? And it's labeled, so I don't really need to label it anything else. That's H of 3 is approximately whatever that is, negative 48 plus 91, 43. But again, Like don't do any more math than you have to. And one more time, you could have left this as your safe stop slope, and it would have shown up right there, and it would have shown up right there, and you know it would be a giant mess if you had that written right here, but it would still be correct, and you'd be fine. All right, so there's part one. Okay, so maybe a crazy problem, but we should get that part done. Part B. Use the second derivative, which I guess means we'll probably need to find the second derivative, to determine whether your answer in part A is an underestimate or an overestimate of the internal temperature. Okay, so I know my temperature is decreasing, so if it's concave up, then my estimate is an underestimate, and if I'm concave down, then my estimate is an overestimate. And again, that's those things that you don't really memorize. You sketch out and kind of remind yourself of what's going on. So I need to figure out its concavity, and then I can use that to figure out if it's an underestimate or an overestimate. Okay, so let's back up. dH dt, they told me, was negative 1/4 h minus 27. Now I want a second derivative. I think before I do a second derivative, I think I want to distribute the 1/4. Because, I mean, maybe that looks a little bit worse, but what's the derivative of 27/4 going to be? That's going to go away, so I don't have to worry about it. So I think it's easier to distribute and then take a derivative. So yeah, this step may look ugly, but the next step's going to be fine. So the second derivative, if I take another derivative, it's going to be negative 1/4 dH dt. So let's see, a couple things we could do from here. We know dH dt at time 3. No, we know it at time 0, which is enough. So I could plug in the slope at 0, and that would tell me the derivative, or the second derivative at time 0. Or I could, that'd probably be the easier way. But what I think most people see is they think, well, I have an expression for dH dt, and this is what you usually do. So let's plug in for dH dt. So negative 1/4 times negative 1/4 h minus 27. This is probably the better way, because now I can say 1/16 h minus 27. So what can I say about my second derivative in terms of positive or negative? Is that going to be a positive or negative second derivative? Is there a way I know it's always positive? There's a statement they gave me in the problem statement that I wasn't sure what it means, but now I know why they gave it to me. Yeah, always greater than 27. I was wondering why that was in there. I didn't really know what that was for. But now that I hit this, I'm like, oh, if h is greater than 27, then my second derivative is always positive. So let's spell it out nice and clear for the grader. If the second derivative is always positive, that means h is always concave up. So answer from A, I mean, we can just phrase it like that, because it wasn't h of 3, it was our approximation for h of 3. So our answer from A is, again, I've got my little pictures to help me remember what this is. So it's concave up is an underestimate. And I think this makes sense. Think about the potato cooling down. Whatever it's headed toward, it's going to like slowly approach that temperature, right? It's going to cool down quickly at first and then slowly cool down after that. It doesn't like fall off and like nosedive into room temperature. So that makes sense. So our estimate is going to be an underestimate. Part C. There's only 3 parts, so my guess is this is going to be kind of crazy, because those felt like fairly straightforward problems. Part C. For t greater than 10, an alternate model for the internal temperature of the potato at time t minutes is the function g that satisfies this thing. Okay, so for the first 10 minutes, it's modeled by h. After that, it's going to be modeled by g. G of 0 is 91. Okay, that's the same as what we did. Find an expression for g of t. Okay, so solve for g of t. And then based on that model, find the temperature of potato at time 3. Okay, this fits what we said earlier. We're going to have to separate and then integrate and then solve for c and then answer the question. So this part C has all of those things in it. So dg dt equals negative g minus 27 to the 2/3. So we want to solve that. Here's my initial condition. It'll tell me what c is, and then I'll plug in time equals 3. So let's see. I need to get the g stuff by itself. So I'm going to divide or move the g stuff over, so that's g minus 27 to the negative 2/3 dg equals, I left the negative on the right hand side, it doesn't really matter. So there's my separate step. Almost always in these differential equations free response questions, almost always you get a point for separating. Seems like very generous. It's the only time I feel like they're that generous. Like, all right, separated, good work. Here's a point. Well done. Now let's integrate. So the right-hand side's easy. That would just be negative t plus c. The left-hand side, okay, this is going to be power rule, because only the negative 1 is the natural log thing. So this is power rule. So g minus 27 to the 1/3 divided by 1/3. And there's no chain rule considerations because the derivative of g would just be 1. Okay, so where am I in this problem? Find an expression for g of t. I haven't done that yet, so I need to solve this for g. So I think I would divide by 3. And then cube both sides. This is just all algebra right now. I suppose I could make that c minus t instead of negative t plus c, but whatever. Cubed and then plus 27. So g of t equals negative t plus c over 3 cubed plus 27. That's still not exactly done yet, because now I need to, right, there was the separate, there was the integrate. Now I need to use 0.91 to figure out what c is. I sure hope they made this problem work for me in terms of like the algebra I'm about to have to do. So 91 equals t is 0, so that's good. C over 3 cubed plus 27. Okay, 91 minus 27 is 64. And you could leave that as 91 minus 27, but like if you safe stop everything, then you kind of have a mess on your hands. So as nice as it is, sometimes it's maybe more helpful to actually do the math. Oh, they have done us a favor here. I can cube root both sides. or raise both sides to the 1/3. 4 equals c over 3. So c equals 12. So now I'm just going to rewrite. That worked out well in terms of spacing. Rewrite g of t, but I know what c is. This is just annoying me. I'm going to write it as 12 minus t over 3 cubed plus 27. You don't have to box anything on the AP test. In fact, graders tell you not to box things because it sort of draws their attention to that when they'd rather read the whole answer. I still like boxing things. It feels like it draws my attention there. Like that's my answer. And then lastly, use that to find the temperature at time 3. This is a great place for a safe stop because all I'm going to do is plug in 3 and walk away, right? Like I don't care what the temperature is. I'm going to plug in 3 and be done. And so, yeah, there's things you could do here. Like 12 minus 3 is 9. 9 divided by 3 is 3. 3 cubed is 27. Nope. 12 minus 3 over 3 cubed plus 27. That's my answer. Thank you very much. I'm walking away. All right, we're at 21 minutes. I took a few minutes introducing that question, so we may have gone a little more than 15 minutes on that one. Hopefully we catch a break on a different one and are able to go a little faster on some other problem. But that was in 2017, that was definitely the problem that people walked out of the test saying, oh my gosh, potato problem. And then a few days later, we worked it in class, and I'm like, that wasn't, I mean, yeah, it was a lot, but we've done all that stuff. So hopefully they eked out some points on that. Okay, what else did we say we were going to do today? Number 2 from that same worksheet. So this was in 2016. Consider that differential equation. First thing I notice about that differential equation is that that's not separable. So this is not going to be a separate and integrate problem because I cannot get those apart. Right? I could like add 1/2 y to the other side, but to separate you almost always have to divide and multiply. That's the only way to separate so that you can integrate. So I don't know what's coming on this, but they can't ask me to integrate this. I mean, maybe in a later calculus class, but not in AB or BC. Part A, find the second derivative. Okay, I can do that. So the second derivative is 2x minus 1/2 dy dx. Is that an acceptable answer? Is that an acceptable answer for part A? Why not? Yeah, it said find the second derivative in terms of x and y. And I haven't quite done that yet. My guess is this is probably just a 2-point part of this, and you probably get 1 point for doing this and another point for plugging in dy dx. And there's another safe stop thing, right? Like, sure, you could distribute the 1/2 or the negative 1/2, and there's not even like terms to, but why bother? Like, you did what they asked you to do. Take your point and move on. Part B. Let y equals f of x be the particular solution. So I'm not going to find it, but there is some particular solution out there whose graph passes through the point negative 2, 8. Does the graph have a relative min, a relative max, or neither at the point negative 2, 8? Justify your answer. Okay, so negative 2, 8. That's like right there. And I'm wondering if it's a relative min or max or neither. So I think I want to find, so for a min or max, that would be if y prime equals 0, and if the second derivative was not 0. right? If the first derivative is 0, and then the second derivative will tell me concavity, which will then tell me if it's a max or a min. So let's check the first derivative, and if we get 0, then we'll check the second derivative. If we don't get 0, then we'll know that it's just increasing or decreasing there, and it's not a max or a min. Before I even start working this problem, I'm guessing it's a max or a min, because that's going to force me to work more of the problem. Okay, dy dx at negative 2, 8. Again, that's using sort of the fancy symbols, but you don't have to do that. You could just plug in negative 2, 8. X squared, so negative 2 squared minus half of 8. Okay, so safe stop doesn't really work here because I need to know if it's 0, so I don't want to just leave it like that. But yes, 4 minus 4 is 0. Okay, so that means there's a horizontal tangent line there. It's a flat spot. Now I need to figure out, like, well, which flat spot is it? Is it concave up and therefore a minimum, or is it concave down and therefore a maximum? So my second derivative, I just covered up, is 2 times, what point am I using? Negative 2, 8. 2 times negative 2 minus 1/2. Negative 2 squared minus half of 8. Oh, we just did this. This was 0. So, my second derivative then is negative 4. Okay, so if the first derivative is 0 and the second derivative is negative, what does that mean? It's concave down, and then you combine that with a flat spot. Dy dx equals 0. Second derivative is negative. Therefore, negative 2, 8 is a flat spot, concave down is a maximum. A relative maximum. Flat and concave down, yes. Again, some people memorize all those different combinations. I don't do that. Like, just think about what concave down, concave up means, and then you can figure out what's going on. And your little pictures, like I'm doing pictures to like convince myself, remind myself, those definitely do not count as like justification or part of your answer. But if it helps you think through what's going on, then by all means do it. Part C. Let y equals g of x be the particular solution to the differential equation, where g of negative 1 is 2. Find the limit as x approaches 1 of that thing. Show the work that leads to your answer. Okay, well, job 1 on limits is like just plug it in and see what happens. So g of negative 1 is 2. Uh-oh. Whoops, I don't want to put 0. 0 over 0. What happens when we get a limit of 0 over 0? What should we do? L'Hopital's rule. So let's say it. So that's indeterminate form. I'm going to use L'Hopital's rule. So the limit as x approaches negative 1. Again, for a free response question, it's better to show your work, make sure they know what you're doing. G prime of x, let's see what that is. Derivative 2 goes away, and then in the bottom, 6 times x plus 1 to the first times the derivative of x plus 1. So let's try again. But I need to know g prime of negative 1. That's the same thing as dy dx at negative 1. And in fact, at negative 1 too. So they gave us an expression for g prime. They didn't call it g prime. They called it dy dx. But if g is a solution to that problem, then dy dx is g prime. Let's see. Negative 1 squared minus 1/2 of y. So that would be 1 minus 1 is 0. Uh-oh. The bottom is going to be also 0, because if I plug in negative 1 there, do it again. Do it again. Indeterminate form. Therefore, use L'Hopital's. So, limit as x approaches negative 1 of the second derivative. But remember, we have an expression for the second derivative, so we can handle this. And in the bottom, let's see, that derivative, that might be easier to rewrite as 6x plus 6. Take that derivative and get 6. So the second derivative at negative 1, the second derivative at negative 1, 2. And I'm going to go back and find the second derivative here, wherever that went. Where did that go? Way back at the top. So 2 times x minus 1/2 times the first derivative. First derivative was 0. So I'm saving myself a little bit of work here. So the second derivative is negative 2. So negative 2 over 6, that's my answer. Yeah, it's negative 1/3, but goodness, yeah, that was a tricky one. L'Hopital's twice, plus kind of recognizing what was going on there. Part D, we don't know Euler's method, so they would not give us part D in terms of AB. That would be a BC part of the problem. So they'd have to kind of redistribute the points. I took a note there. We started this problem at 23 minutes. We're now at 32 minutes. So that one only took 9 minutes, which is good because that first one took a little longer. Again, you have 15 minutes per problem on average, so you can spread that out and apportion that how you like. Okay, I'm going to stop the video there, and then we'll start it up for a different one in a moment.